Started, and we're skipping construct the understanding. Take out your highlighter. And we're going to highlight the definition of a reference angle. And maybe off to the side, you write a little note. It's always positive and between 0 and 90 degrees. The angle to the nearest x-axis. So I have examples. If your standard angle is 35 degrees, your reference angle would be 30 to 5 degrees. But if you had an angle of 145 degrees, and remember, all those red angles are in standard position because they start on the positive x-axis. So we would say that the angle of 145 degrees has a reference angle of 35 degrees. The angle of 215 degrees also has a reference angle of 35 degrees, and an angle of 325 degrees also has a reference angle of 35 degrees. So the question is, how do you find a reference angle? Does it make sense that in quadrant 1, if I tell you an angle in quadrant 1, then the reference angle is identical to the angle? If I tell you an angle in quadrant 2, your reference angle always has to add up to 180, because halfway around is 180 degrees. So we're going to use 180 to figure out a lot of things about reference angles. In this situation, does it make sense that your reference angle would be 180 degrees minus the 170 degrees, or 10 degrees? And if I gave you an angle in quadrant 3, (220 degrees), and you were asked to find out what is its reference angle right there. Does it make sense that your reference angle in this case would be 220 is too much, but you'd have to subtract 180 and you'd be left with this little part? So in this case, it'd be 40 degrees. And finally, in quadrant 4, if I gave you an angle in quadrant 4 and said, can you find the reference angle for 300 degrees? You're trying to find this angle right there. All the way around the whole circle is 360. So in this case, 360 is too much. How much too much? If I subtract the 300, does it make sense I'd be left with 60 degrees for my reference angle? And the reason reference angles are important is as follows. We're going to go back up to the examples that we have. Okay? And if I have 35 degrees, I could draw a straight line down and make a right angled triangle. And my calculator has 35 degrees built into it. So for example, if I choose tan, and I say tan, maybe, of 35, it gives me 0.700. Tan of 35 degrees which is approximately 70 over 100 or 7 over 10. Maybe I'll use 7 over 10. What that means is that wherever I draw this line to make a triangle, the ratio of the opposite side over the hypotenuse has to be equivalent to 7 out of 10. So I might have drawn it that it was exactly 7 out of 10. It could be 70 out of 100, make a much bigger triangle. But no matter what numbers are on the opposite over the adjacent, for 35 degrees, it will always come out to 0.700. Now, if I drew this same length of a line over here, where this was 7, can you see that that would make the exact same triangle just flipped over? And so what our calculator does for us is it says, well, if I type in tan of 145 degrees, watch what happens. I get the exact same number, but this one is negative. Weird. And if I drew this exact same triangle with this reference angle, and I try on my calculator tan of 215 degrees, I get the exact same answer, but this one is positive. And finally, if I drew the exact same triangle in quadrant 4, my calculator, again, when I type in tan of 325 degrees, I get the exact same number and negative. Which leads us to our next idea, okay? We are now, in grade 10, you only did trigonometry with right-angled triangles, and with right-angled triangles, you never had an angle go bigger than 90 degrees. But we are now extending our trigonometry beyond, because tan of 145 degrees is never inside of a right-angled triangle. And yet your calculator gives us an answer for it. And the idea is this idea based on reference angles. It says that you could draw that same triangle in quadrant 2. But now if we think of coordinates, can you see that your opposite side is still positive because it's going up? But now my adjacent side is going to the left, it would be negative. And so because of that, when I do tan of 145, I got a negative answer. In quadrant 3, I'm going down. So this length would be negative. I'm going to the left, that would be negative. And a negative over a negative makes positive. And so for tangent in quadrant 3, it was positive again. And same thing, if you went to quadrant 4, this side would be positive, this side would be negative. And so tangent is negative. So what we found for tangent this one was positive, this is negative, this quadrant's positive, and this one's negative. We're going to see what happens with sine. We're going to look at all 4 quadrants. We'll do the 35 degrees. If I would do sine of 35 degrees, I get 0.57. If I do sine of 145 degrees, I get positive. Maybe sine is always positive. I'll try sine of 215. Oh, that one's negative. And sine of 325. So once again, sine, which is the opposite over the hypotenuse, would be the same for all of those angles, because no matter where you are, you could make a triangle with your reference angle, and it would make the exact same triangle. But now the opposites and adjacents switch, and we notice this. Sine was positive here, negative here, and negative here. We'll do one more with cosine. So if I do cosine of 35 degrees, positive. Cosine of 145 degrees, negative. Cosine of 215 degrees, negative. And cosine of 325. So notice the numbers stayed the same again, because they all had the same reference angle. But for cosine, it was positive here, negative here, positive there. And this becomes really important. For trigonometry, once you go beyond 90 degrees, you need to be able to tell where things are positive and where they're negative. And instead of memorizing these three charts, there is an easy way to remember. And it goes like this. In quadrant 1, they are all positive. So we put the letter A in quadrant 1 to symbolize that sine, cosine, and tangent, all three, are positive. In quadrant 2, only one of them is positive. You need part 2? Need an eraser? Which is the only one that's positive in quadrant 2? Sine. So we put an S here. That S says sine is the only one that's positive. Both cosine and tangent, as a result, are negative in quadrant 2, which is the only one that's positive in quadrant 3. And finally, in quadrant 4, only cosine is positive. Okay? And they call this the cast rule, because it spells the word cast, and that's easy to remember. They should call it the Asticot rule, but it doesn't ring as nice, because you should start with quadrant 1. But Asticot, just, so it got called the cast rule. I mean, you could probably spell different acts backwards, but then you might get confused with an axe. So I don't know. It's called the cast rule as a result. And that rule tells us where things are positive and where they're negative. Because we're going to get questions which move beyond our 90-degree triangles that we've done so far. Okay? You can also have angles that are in standard position that go in the negative direction. So if I went this way, this might be negative 100 degrees. Can someone tell me how big this reference angle is? That reference angle would be positive 80 degrees. Reference angles are always positive and always between 0 and 90 degrees. Okay, so this is the huge setup for trigonometry moving forward in grade 11 and grade 12, because we move beyond just triangles and SOHCAHTOA. Right now, from the introduction, you can already circle in your homework questions 3, 4, 5, and 7. And we will go to example 1. We have the point -2, -4 is is on the terminal arm of an angle in standard position. So -2 this way, -4, 1, 2, 3, 4. There is -2, -4. This is the angle in standard position, theta. The question is asking us to determine sine of theta, cos of theta, and tan of theta. This is trigonometry. The main strategy in trigonometry, it's going to blow your mind, is drawing a triangle. Wow. The main strategy in trigonometry is drawing a triangle. The triangle that you want to draw will always include your reference angle. So I'm going to draw a line straight up back to my x-axis, making a right angle triangle, and that will, in green, make a reference angle. Now we're going to start by labeling the lengths of this triangle just with whole numbers. Would you agree that this length here, right here, has a length of 2? And this length down here has a length of 4? Because of the point -2 and -4. I always like to label the lengths of my triangle with positive numbers. You'll see sometimes people might label that as -2 because it went 2 to the left and -4 because it went down 4. But I just like to label them with positive values. How could you find the hypotenuse? A squared plus b squared equals c squared. Square root of 20. Can you simplify this? It would be 2√5. So I now know that this length right here is 2√5. Part A, when it says determine the primary trig ratios, they want you to find sine of theta, cos of theta, and tan of theta. Now, in a right angle triangle, you know that sine of theta is the opposite side over the hypotenuse. Now, theta isn't part of a right angle triangle. Only its reference angle is. So we use the reference angle and say that sine of the reference angle would be 4/2√5. And we would think of our cast rule and say, we are looking right now in quadrant 3. Should sine be positive or negative in quadrant 3? It should be negative, so we add a negative. And now we would lose a half mark for not simplifying. Can you see that the 4/2 can be simplified? Can you see also that in order for it to be simplified, we'd have to use our radicals unit and rationalize the denominator? So after simplifying, you are going to get -2√5/5. Are you okay with the -2? Because 4/2 is -2. And I multiplied by the top by a √5, that's why there's a √5 on top. And on the bottom, if you multiply √5 times √5, you're going to just get √25, which is 5. And so that's rationalizing the denominator for sine. Cosine will be adjacent over hypotenuse. It will also be negative in quadrant 2. In this case, we would have to rationalize the denominator again. And tangent is opposite over adjacent, and tangent is positive in quadrant 3. So that cast rule is going to tell you if your ratios should be positive or negative. Now, part B, we need to find the actual angle. In order to do that, you have to first find the reference angle. And finding the reference angle is based on the same trigonometry you did in grade 10. You have that triangle. With this triangle, you could find the angle by either using sine, cos, or tan. If you're finding a reference angle and you're using an actual triangle, the negatives go away completely. Because in an actual right angle triangle, there's no negative sides. They're all positive sides. If I was using sine, cos, or tan, based on the numbers, I probably would use tangent, because it doesn't have any square root. So I would start by saying, I know that tangent of my reference angle is opposite over adjacent, which is 2. How do you find an angle using your calculator? You find an angle with tan inverse. So my reference angle, I would type into my calculator tan inverse of 2. I go second, tan inverse of 2, and I find out my reference angle is 63.43. So my actual angle, if this reference angle is 43, what is the big blue angle going to be? Can you see that you have to go 180 plus your reference angle? I might write that out first. Some people memorize that as a formula for quadrant 3. I think if you just look at the picture, you don't have to memorize it. It should make sense to you that if I want to find this big angle theta, I would have to go 180 to get halfway around, and then I have to add my reference angle to get the answer. You're going to find if you try to memorize the formulas for every quadrant, you're going to mix them up. If you just think about drawing the picture, it's going to make sense, and you'll never have to memorize it. You'll just be able to, oh, quadrant 3 makes sense that I would go 180 and add my reference angle. So if I go 180 plus the 63, am I supposed to round in this one to the nearest degree? Will give me 243 degrees. These are the kind of questions that we're going to get with solving. Okay? Now, if they told me, if you started off with your sine being negative 2 root 5 over 5, and you went to your calculator, if you're finding a reference angle, you go sine inverse, but always the positive. So I would write positive 2 square root of 5 over 5. And notice that I get the exact same reference angle than if I used tangent or cosine. But it's really important that when you're finding a reference angle, you're thinking about the actual triangle and only using positive values. Because watch what happens if I add a negative. I'm going to retype this whole thing and say, well, what happens if I had a negative in there? Well, when it solves for it, it no longer gives you an answer between 0 and 90. You're like, oh, but it's the same number. Wouldn't that be fine? Well, watch this with cos. Cos gets messed up. Okay, first of all, I'll do it right. So if I am solving cos inverse of square root of 5 over 5, I should get exactly the same reference angle that I did with sine and cosine. And I do, I get 63.434. But what happens if I accidentally included a negative? I get 116 degrees, something completely different. So it's going to be really important when you're finding your reference angle. You're going to hear me say this over and over and over again. But when finding a reference angle, you always use positive values because you're thinking about the actual triangle with actual side lengths. You are actually going back to grade 10 trigonometry and just using your basic SOHCAHTOA. But now that you're in grade 11, you realize that this angle isn't in quadrant 1, it was in quadrant 3, so I had to do 180 plus my reference angle in order to find it. Circle questions 6, 10, and 11.